So as I said on Thursday, I hope you enjoyed the long weekend. This unit's kind of short. There's not a lot in there. I gave you the outcomes there on Thursday. If you didn't get them, you should get a copy. Basically, there's 7 types of problems, and you need to be able to do them all. Okay, and then a couple of other outcomes that are related to them. So today, draw the horizontal and vertical velocity vectors for a projectile at various points along the path, which you'll find very simple, I'm sure. And calculate horizontal and vertical components. You thought maybe you had gotten away from using components, but that's not true. Let's begin. Earlier we discussed the vector quantities velocity and acceleration. Since only horizontal and vertical motion is considered, we did not need to know about vector addition or techniques of vector resolution, but for objects projected at angles other than straight up or straight down, we do them. We've already done vector addition and whatnot, so basically we are simply going to be combining horizontal and vertical together. Basically is what it is. It's sort of the reverse of what we did before. You might remember when we did in the dynamics unit, we were pulling at an angle and you had to find the horizontal and the vertical component. Same idea here. Sort of pulling them apart in that same idea. So a projectile is any object that is projected by some means and continues in motion by its own inertia. That's kind of important. You might remember the free body diagram that we did there back in the last unit with the football having already been punted, and the only force that's actually acting on it is gravity, right? So that's the definition of a projectile. Projected by some means and continues in motion by its own inertia. A cannonball shot from a cannon, a stone thrown into the air, or a ball that rolls off the edge of a table are all projectiles. It does not need to be at an angle. The angle of 0 is equally as good as an angle of 30 degrees or 45 degrees or even 90 degrees. It's all equal projectiles. Something wrong with that one, Sophie? These projectiles follow curved paths that at first thought seem rather complicated. However, these paths are surprisingly simple when we look at the horizontal and vertical components of motion separately. And so that's the key idea there. If there's one main idea in the whole unit, and that is that the vertical and horizontal components have to be looked at separately. And you really have to, depending on what the question asks, figure out which velocity component do I need to worry about here. The horizontal component of motion for a projectile is no more complex than the horizontal motion of a bowling ball rolling freely along a level bowling alley. If the retarding effect of friction can be ignored, the bowling ball moves at a constant velocity. And as you probably saw in grade 11, when an object moves at constant velocity, if those time intervals are the same, then the distance between them should also be the same, and in fact they are, right? And the same is true when you project something. You remember from Thursday when we had the picture of the guy throwing the tennis ball in the garbage can, and we looked at the picture and we decided that those horizontal distances appeared to be very much the same. Interestingly enough, the horizontal component of motion for projectile is completely independent of the vertical component of motion. Each acts independent of the other. There's that idea again. Their combined effects produce the variety of curved paths the projectiles follow. The multiple flash exposure of figure 2 shows equally timed successive positions for a ball rolled off a horizontal table. Investigate the photo carefully. There's a lot of good physics there. The curved path of the ball is best analyzed by considering the horizontal and vertical components of motion separately. There are 2 important things to notice. The first is that the ball's horizontal component of motion doesn't change as the falling ball moves sideways. The ball travels the same horizontal distance in equal times, between each flash. That's because there's no component of gravitational force acting horizontally. Gravity acts only downward, so the only acceleration of the ball is downward. The second thing to note from the photo is that the vertical positions become farther apart in time. The distances traveled vertically are the same as if the ball were simply dropped. It's interesting to note that the downward motion of the ball is the same as that of free fall. Now, actually, you've got a slightly different picture than mine. I was fixing up these notes yesterday, and I discovered a better picture that was a little bit better there, so you could see it better up there. And I'd already run that stuff off, so next year's group will get a better picture. But you'll notice here that this line, this white line right here, right, shows those balls, and they are where vertically. They're equal, exactly. And are they the same time flash, the same instant of time? You can just count back. 1, 2, 3. There's a couple over top one another. But you'll definitely see that if you look carefully, that they are equal. And in fact, that is true all the way down with a small margin of error. Right? If I drew lines like this, and if I drew them straight and measured them, they should be what? Equal the same distance apart, right? Equidistant, as the math people like to say. Equidistant. The path traced by a projectile that accelerates only in the vertical direction while moving at a constant horizontal velocity is called a parabola, which you are familiar with from math. When air resistance can be neglected, usually for slow-moving projectiles or ones very heavy compared to the forces of air resistance, the curved paths are parabolic. So here's a question. Oh, Brandon's got one before I get to ask. Where do the lines start and end on the yellow line? Yellow balls.
Like, do they begin at the end of one and, like where is the distance? What are you measuring with the
Okay, so what I did was I drew a line straight up from the, we'll say the front of the ball, the right-hand side of the ball, right? And I did that for everyone, right? And so the distance that I'm talking about is, let me see if I can do it in a different color here. How do I do that? In yellow. So I'm talking about this distance here, Brandon. That distance there to that distance there to that distance there. And I didn't do a very good job of drawing them straight up down, but no. The right side of one ball to the next right side of the next ball, not the top. The right hand side. Right. The distance between there and there. The ball's going this way, right? Well, it's actually going down. But it travels. How far does it travel to the right in that time period? It travels that yellow distance right there.
Okay.
Okay.
Oh, okay. I get it.
Okay.
Really accurate.
No, absolutely, Jake. Good point. We could have drawn, and I'll draw them in yellow again. I could have drawn from, I guess it's going to be red, from there to there to there, right? That fact should exactly be the same distance as before, right? You can go middle of the wall, 3/4 of the way, whatever, right? Absolutely. Yeah. Most people would put it in front, that's all. Okay, so here's the question for you that you're going to need the clickers. I guess I'll have to wait till you guys get signed in. At the instant a horizontally held rifle is fired over a level range, a bullet held at the side of the rifle is released, drops to the ground. Which bullet, the one fired from the range, downrange, or the one dropped from rest, strikes the ground first? So come on down and grab your clickers. Oh, thank you. Well, yeah, it's not to scale, Jake, purely for illustrative purposes. So one bullet is fired straight sideways, one is dropped. Which one hits the ground first? What's your idea again? Upwardly moving projectiles. Consider a cannonball shot at an upward angle. Pretend for a moment that there is no gravity. Then, according to the law of inertia, the cannonball will follow the straight line path shown by the dashed line in figure 3. So, if there was no gravity, we would simply do that, right, in a straight line. But there is gravity, so this doesn't happen. What really happens is that the cannonball continually falls beneath this imaginary line until it strikes the ground. Get this, the vertical distance it falls beneath any point on the dashed line is the same vertical distance it would fall if it were dropped from rest and had been falling for the same amount of time. I'm going to explain that again. If I were to drop a ball at this height and let it drop for 2 seconds, it would drop 20 meters. The cannonball also drops 20 meters, even though it's doing what? Going up. Okay? It doesn't matter what the vertical component is. It's going to accelerate down. It's going to drop. It's going to lose 20 meters of height, whether it's dropped from that height or whether it's projected and it's at that particular instant. This distance is given by d is equal to 1/2 gt squared, where t is the elapsed time, which would be exactly the formula that we could use for our brand new g-balls here. How come this looks suspiciously like d equals vit plus 1/2 at squared with two differences? I got no a in there, I've got a g. What's that? Yeah, just gravity is the acceleration. And what happened to the vit part? Why gone? Because the initial velocity is 0. Okay? So we could take the new g-balls, drop them from a known height, right? And then with the time, calculate g. Should we try right now? So the point there is, though, that it doesn't matter what speed it has, it's still going to fall at 20 meters. So we can put this another way. Shoot a projectile skyward at some angle and pretend there's no gravity. After so many seconds t, it should be at a certain point along a straight line path. But because of gravity, it isn't. Where is it? The answer is that it's directly below this point. How far below? The answer in meters is 5t squared, or more accurately, 4.9t squared. 1/2 is 9.8. Note another thing from figure 3. Question? The cannonball moves equal horizontal distances in equal time intervals. That's because no acceleration takes place horizontally. This distance here between 1 second and 2 seconds is exactly the same as that distance there. How come? What's the horizontal acceleration? 0. The only acceleration is vertically in the direction of Earth gravity. The vertical distance it falls below the imaginary straight line path during equal time intervals continually increases with time. The horizontal velocity is constant, in fact. Figure 4 shows vectors representing both horizontal and vertical components of velocity for projectile following a parabolic path. Notice that the horizontal component is everywhere the same and only the vertical component changes. Note also that the actual velocity is represented by the vector that forms the diagonal of the rectangle formed by the vector component. So what they're saying is here, there's the actual velocity. Oops, I guess that's true. And it's tangent to the path. And then we have horizontal components, which I will draw in blue. And you'll notice that the horizontal components are all what? All the same. And the vertical components drawn in black, well, they do what? They're positive to begin with, 0 at the peak, and then negative later on. How come? Because there's vertical acceleration. That's equal to what? Gravity, minus 9.8. Note that the actual velocity vector is represented by the vector that forms the diagonal of the rectangle formed by the vector components, right there in red. At the top of the path, the vertical component vanishes to 0. So the actual velocity there is the horizontal component of velocity at all the other points. Everywhere else, the magnitude of velocity is greater, just as the diagonal of a rectangle is greater than either of its sides. Figure 5 shows the path traced by a projectile with the same launch speed but at a steeper angle. Notice that the initial velocity vector has a greater vertical component than when the projection angle is less. This greater component results in a higher path, but the horizontal component is less, so the range is less. So because the angle is steeper, the horizontal component is not as great, therefore the ball doesn't what? Travel as far. Thank you, Mr. Thacker. Those are the names? So the reason it doesn't go as far is because the horizontal component isn't as great. Does that make sense? Give me a bit of a nod here, you guys. I'm starting to wonder if anyone's actually awake out there. Yeah? Okay. Figure 6 shows the path of several projectiles all having the same initial speed, but different projection angles. This figure neglects the effect of air resistance, so the paths are all parabolas. Notice that these projectiles reach different altitudes or heights above the ground. They also have different horizontal ranges or distances traveled horizontally. So 75 degrees is up and down, 60 degrees is up and a little farther, 45 degrees even farther, and so on. The remarkable thing to note from figure 6 is that the same range is obtained from two different projection angles, angles that add up to 90 degrees. Look at 75 and 15 land in exactly the same place. Do they take the same amount of time? How confident are you of that, Joey? Because you said probably. Now he's gone silent. What do you think, Darren? Same amount of time or different amount of time? It's not really a trick question. It really is. Same amount of time, Jake? Jason, what say you? Same amount of time?
one that's starting at 75 degrees and have a higher vertical velocity,
Right.
take longer to reach that.
Not exactly. It's gonna. You can tell it has a greater vertical component because it actually goes higher, which means it's going to take longer to get to its peak, which means it's going to take longer to get down. Right? Just think about it. If all I do is I just toss this ball, if I just toss it and land it like 10 feet away, how long is that going to take? Oh my gosh, time I get shouldn't it, right? Hardly any time at all. But if I throw it really, 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 really high and it magically lands in exactly the same spot, which one's going to take longer? Yeah, the one that goes like crazy high. I couldn't do that. There's no way. I said it wasn't a trick question, but maybe it was. I guess I don't know. Figure 7. Maximum range is attained when the ball is batted at an angle of nearly 45 degrees. In cases where the weight of the projectile is comparable to the applied force, when a heavy javelin is thrown, the applied force does not produce the same speed for different projection angles. So heavy objects, this isn't true for. But regular, sort of everyday baseball size, weight size kind of things, 45 degrees. Okay, now, Chris knows from the golf course that golf balls do not travel in parabolas, do they? They go up, and especially if you hit like a 7 wedge or a 9 iron or something like that, they go up in the air, and then they actually, the air resistance kicks in, and it actually almost drops straight down, doesn't it? Which is what you want to do, so that it doesn't roll, right? So yes, when there's air resistance, it's not a parabola, and everything else is sort of out of whack, okay? Would the Mythbusters had to deal with air resistance in their projectile? They probably did. There's not a lot of air resistance on a bullet, I wouldn't think. It's pretty aerodynamic, but on the other hand, it's traveling at a high rate of speed, and so air resistance is significant. Okay, here's the were you listening part. A projectile is shot at an angle into the air. If air resistance is negligible, in other words, 0, what is its downward acceleration? And I think you have to actually type in a number. Minus 9.8. Downward acceleration. Oh, Jason wants to.
It's saying downward acceleration, so it's.
So you're saying the negative doesn't need to be in there?
It should be a positive.
Lawyer in the making.
It's like half the velocity.
I'll better change that to vertical. So would that satisfy you? Fair enough. What about its horizontal acceleration? Uh-oh. Were you listening? Oh, Joey with his mad science laugh. Horizontal acceleration. I really do have to get that Jeopardy theme song, so I can just press. Okay. Correct answer is 0. That is correct. What is the horizontal acceleration? A big fat 0. How come? What force is providing the acceleration down? Gravity. What force would be applying the acceleration sideways? There is none. Therefore, the acceleration is 0. Remember that whole deal about the distances between, right? This whole deal? The distances are the same. How come? It's not speeding up. Constant velocity. It's not speeding up. Here, the horizontal component is always the same. Therefore, the acceleration is big fat 0. Oh, boom. Now here's the next step of thinking. At what part of the path does the projectile have its minimum speed? When is it actually going the slowest? Is it at the start? Is it at the end? And I don't mean like after it's landed and it's been sitting there for 27 minutes. Is it at the peak? Or is the speed, and I say speed, lawyer boy, not velocity, speed, the minimum? What do you think? Correct answer is, yeah, C. I've sort of trained you to say it's always the same, haven't I, with lots of other things. Why is it at a minimum there? Because there's no vertical. If the horizontal was, say, 5, always 5, right? And just give me a sec, Brandy, right? And if the vertical here is, say, well, let's make it 4, because then we can do it. If I make this 4, 4, 4, 4, 4. If I make this 3, then this is going to be, the overall is going to be 5. But here, the vertical is 0, so what's the overall? Only 4. Anytime there's a vertical, the speed is going to be greater than 4, right? But as soon as there's no vertical, then the overall speed is only 4. Right.
So that acceleration doesn't stop. That gravity doesn't stop.
It doesn't.
I'm so confused. Can you please?
Why does the fact that gravity doesn't stop have anything to do with this? You don't know? Or Jason?
It's because it's using speed, that's distance and not displacement.
If the only reason I had to use speed instead of velocity was because there'd be some lawyer boy out there who would say that, well, here the velocity is positive because it's headed up, and here the velocity is negative because it's headed down, and negative is less than positive, and therefore, so that's why I said speed. Jake?
Would it be because gravity is present all throughout the path, so the higher speeds in the beginning are with gravity anyways?
Yeah, absolutely. I mean, gravity's always there, right? What I'm trying to say is, if the horizontal is 4, and there's a vertical of 3, what is the overall velocity? It's 5, 3, 4, 5 triangle, right? But at the very peak, what's the horizontal? 4. What's the vertical? 0. So what is the overall? 4. There's no vertical to add. It's at its smallest speed right at the peak. Wait, hey. Still some confusion? I'll let that soak in. Maybe we'll come back to that. If air resistance is small enough to be negligible, a projectile will rise to its maximum height in the same time it takes to fall from that height to the ground. The time up is equal to the time down. That's what they're saying there. Time up is equal to time down. This is because its deceleration by gravity while going up is the same as its acceleration by gravity while coming down. The speed it loses while going up is therefore the same as the speed it gains while coming down. So the projectile arrives at the ground with the same speed that it had when it was projected from the ground. You see all those news reports where rebels somewhere, they're always, they win or something or other, they win a battle and they're firing guns into the air. Is that a good idea? No. Why not? It's coming down as fast as it left that gun. They might as well be standing like right in front of it. They're shooting it straight up. Because if there's no wind, it's coming down as fast. Bad idea. If an object is projected fast enough so that its curvature matches the curvature of the Earth and it is above the atmosphere so that air resistance does not affect its motion, it will fall all the way around the Earth and become an Earth satellite. This interesting topic we just treated in the UCM, and we talked about it in grade 11. Remember we had the big giant kill and you dropped the ball at increasing, or you fired it at increasing speeds, and eventually you throw it so far that it what? Literally falls all the way around the Earth. Remember that diagram from grade 11? Okay, same idea. Okay, let's have some fun. Are you ready? Okay, so when you're drawing these in, what's the one thing, I guess there's several things to remember, but what's the first thing? Is that the horizontal component should be the same, or within like a millimeter or two of each other, right? Here, the vertical should be large and up. Here it should be, well, not quite as large and up. Here it should be non-existent. Here it should be the same length as that one, but down. And here it should be the same length as the first one, but down, right? Is that what you had, more or less? If the velocity of the ball in the second frame is 10 meters per second at 30 degrees above horizontal, calculate the horizontal and vertical components at that instant. The horizontal component is simply going to be this one right here. If this is 30 degrees, it's going to be what? 10 cos 30. And I don't have the answer. What's 10 cos 30? 5. I think you're right. Did you get that? Do you know why it's 10 cos 30? It's 6?
10 sine 30.
Oh, 10 sine 30. That makes sense. 8.6. Okay, so it's simply, right, there's the angle right there, adjacent, right, cosine. It's exactly the same as last unit, right? Nod with me. Yes, I get it. If you don't, find out. Don't wait. What is the vertical velocity component at the peak? It's okay to be wrong. Thank you, Chris. 0. Vertical velocity component. It's not going up at the peak. What's the horizontal velocity component at the peak? It's 8.6. How come? Because the horizontal is what? Same throughout. Constant. What is the vertical acceleration at the peak? Minus 9.8. Right? And what's the horizontal acceleration at the peak? 0. In fact, the horizontal acceleration throughout the entire trip is 0. Did we do this? Did we draw horizontal and vertical velocity vectors for a projectile at various points along the path? Did we do that? Did we calculate horizontal and vertical components? Yes. You should be able to do it too now. If you can't, come and see me. Let's get it figured out. Okay.